Welcome. In this class, we shall be looking at differentiation. And at the end of this class, you should be able to understand what differentiation is all about. And before we go into the calculations and rules guiding differentiation, I would like to introduce us to the concept of differentiation. What is differentiation? Differentiation is also known as derivative, and it is a way to check how changes in the values of an independent variable, say x, results in a corresponding change to a dependent variable, f(x) or f of x. And this is the notation we use to represent f of x, meaning a function of x. Let's say we have an expression like this: 3x to the power 4 plus 5x to the power 3 plus 2x squared plus 3x plus 7. Now, this is an expression made up of an independent variable, x. So we have another variable, y. And this variable and this expression become an equation if and only if we introduce the equal to sign. It becomes an equation. So we are equating y to the expression we have on our right hand side. And from this equation, we can say y, which is on the left hand side, is dependent on the values of x for its own value. So when we put any value of x into this equation, we'll get the value for y. Now, in this case, we could term y to be a function of x. Y is a function of x. Therefore, y is a dependent variable. Now, let me introduce one concept to us in differentiation. In differentiation, we use the notation of a d to represent changes. Letter d is used to represent change in differentiation. And derivatives are represented, as in our example above, using y and x as an example. Y being a dependent variable and x being the independent variable, will represent this derivative as dy dx, dy over dx, or simply put, dy dx. So dy dx is the rate of change of y with respect to x as x tends towards 0. What this implies is that with dy dx, or with differentiation, we are able to determine the instantaneous rate of change of one variable with respect to another. To drive this point home, I would like to use the concept of a line. Say we have a line, and this line is dependent on several properties. For number one, we could use the length to qualify the line, the thickness, and even the color and the nature, whether it's a broken line and all that, to qualify this line. But for this particular example, I would like to use the concept of length. So our line in itself can be termed our dependent variable, f of x. And this line is dependent on length. I said I'm going to use length in this example. So length in this case is the x, the independent variable. Now, this line, if this line grows and it is growing, what differentiation is interested in is the rate of this growth, the rate of the growth. How long does it, how fast is this line growing per time? Rate of change is what differentiation is looking out for. Let me drive the point home using the equation of a straight line. Equation of a straight line. We remember that for our graphs, we'll find out that the equation for a straight line is given as y is equal to mx plus c. Y is equal to mx plus c, where y is our dependent variable, as we stated earlier, and then m is the slope of the graph, and then x is the independent variable, and then we could say C is our intercept. C is our intercept. Okay, based on this, let us draw a simple straight line graph. We have our y-axis, we have our horizontal or x-axis, and then so we have a straight line running from the origin. We have our y-axis, x-axis, and a straight line running from the origin. Good. Based on this graph, we can see that our intercept is equal to 0, because our intercept is where this straight line cuts across either the y-axis or the x-axis. That gives us our intercept. So this is coming out from the origin, so intercept is equal to 0. We could accurately write this graph's equation to be y is equal to mx, but that's not what we are driving at now. So based on this graph, imagine that we have a point on this graph, and let us call that point P. Okay, point P corresponds to a point on the y-axis. Let's call that point y1, and it has a coordinate on the x-axis of let's call that place x1. Now, say we also have another point Q. Point Q has a corresponding point to the y-axis. Let's call that y2, and then it has a corresponding point on the x-axis. Say let's call that x2. Now, these 2 points form a difference triangle. They form a difference triangle. Now, based on these 2 points, we can calculate our slope for this line. And remember, the formula for finding slope we say is slope m is equal to change on your vertical axis over change on your horizontal axis. Remember, this straight line runs through, and as it's rising this way, this is like your resultant having an equivalent to your y-axis and an equivalent to your x-axis. So we are looking at it, sometimes some people call it rise over fall. So we're looking at the change on your y-axis over your change in the x horizontal axis. So we can say y2, change in the y-axis is y2 minus y1 will give us the change in the y-axis, and that is going to be over the change in our x-axis, x2 minus x1. Good. So x2 minus x1. So our y2 over y1 all over x2 minus x1 we say is slope. Remember, one thing we said was slope is equal to change in y over change in x. Remember, differentiation says we use the notation of a d to represent change. So we can now rewrite this slope as m is equal to dy over the x, which is dy dx, meaning that our slope of our straight line is the differential of y with respect to x will still give us our slope. So differentiation is a very good tool to measure the rate of change of different things, either in motion or growing. Rate of change, different things that are changing. We use differentiation as an important tool to measure rate of change. Now, this is a simple graph, and we can see that the rate of change is constant. I'll use on that graph now to explain what I mean by that. Okay, let's look at this graph. We have a curve. Remember, our first graph we had a straight line, but now we are having a curve. When we have a curve, it means that the slope is not uniform throughout this graph. In our first graph, we had a uniform slope. What does that simply mean? Let us look at this table, for instance. We have x. For every rise in x of one value, we have a corresponding rise in y. Twice that the value of x. Now, if we look at x, for each interval of x, we find out that x changes uniformly. From 2 to 3, we have a change of 1. From 3 to 4, we have a change of 1. from 4 to 5 we have a change of 1, and from 5 to 6 we have a change of 1, meaning that the rate of change on your x-axis is constant. The same thing applies to the y-axis. For each of the rise in y, from 4 to 6 we have a change of 2, from 6 to 8 we have a change of 2, from 8 to 10 2, from 10 to 12 we have 2. So we can see that we have also a constant rate of change on your y-axis. Therefore, if we should plot a graph of y against x, in this case, we would have an identical graph to what we had in our first example, a straight line, telling us that the rate of change of y with respect to x is constant. But in this particular graph, we have a curve. This depicts that the rate of change in this particular graph is not constant. Also, on our straight line graph, we were able to determine the slope of the graph by picking any 2 points on the graph and then taking the slope or the rate of change on those 2 points. But if we do the same thing here, we would not get a very accurate result. Rather, if we rule a line from point Q to P, if we rule a line from point Q to P, like we did in our former graph, if we rule a line from point P to Q, if we take the slope of this line, by the way is called the second line. If we take the slope of this line, what we would get from calculating that slope will give us the average rate of change of this particular graph. Like we said before, the rate of change of this particular graph is not constant throughout the graph. So differentiation is a good tool for us to know what the rate of change per time, the rate of change on the point P, different from the rate of change on the point Q, and their slopes will be different. So that slope that we're actually calculating is giving us the rate of change at an instant, at a particular point. Now, for this particular graph, if we want to find the rate of change at point P, we'll be asked to look for the slope at point P. So how do we take the slope at point P? Usually, we'll draw a tangent to point P. We'll draw a tangent to point P, and this tangent is where we now take our slope. So based on this tangent, we can bring our difference triangle, and then we could now draw our points, corresponding points of the triangle to the y-axis. We label that y1. Corresponding point to the x-axis, we label that x1, and then corresponding points to the y-axis for the upper limit, we name that part y2, and corresponding point for the upper limit on the x-axis, we call that x2. So in the same vein, we still take our slope as y2 over y1 over x2 minus x1 to get our slope. But with differentiation, once you use your tool differentiation, you are able to get what you just need is the equation, and then you are able to get your instantaneous rate of change at any point on the graph. At any point on the graph. So now that we've understood the concept of differentiation in relation to rate of change, in our next class we shall be looking at the laws and the rules guiding differentiation.